It got down to minus 12 Fahrenheit or minus 24.5 Celsius before my mom and dad's 3-ton cold climate heat pump required backup heat. So first of all, stop saying that heat pumps don't work in cold weather. That is outdated information. Cold climate heat pumps are a thing, and they actually work. Now, hello. I wasn't sure if I was going to make this video or not, but this is a very complex topic. Anything HVAC is, but especially heat pumps, especially sizing. And, you know, I couldn't communicate everything. I mean, the video's over an hour long, so it's not like I could hedge against every particular wonky thing that I might imagine people would say, but there were some that just keep coming up, so I do want to address them on Kinextras at least. So yeah, here we are. Okay, so the first thing that I want to touch on is something that I honestly didn't explain because I've explained so many times in other videos, and it bit me in the butt because a lot of people are making the same very common mistake, which is confusing power and energy, which gets particularly wonky when we're talking about efficiency. So a comment that I saw multiple times, and I've responded to several of them, was that if your furnace only needs to run a quarter of the time, isn't that good? Wouldn't you be spending more money on a furnace which needs to run longer? I hate to be blunt, but that is not how that works. Not at all. Now, I'm going to tell you an anecdote later about an HVAC professional who also didn't know this, so don't feel too bad. I mean, he might have been lying, but don't feel too bad. If my furnace were half its size, if I only had a 30,000 BTU per hour furnace, then it would need to run for twice as long as my current furnace. But for every hour that it runs, it's burning half as much fuel. It's putting out half as much energy. That's what matters. The annual fuel utilization efficiency for gas-fired stuff is the only number that matters. There's probably some wonky differences with cycle times, but you don't care about runtime at all. Runtime is irrelevant. It's just the AFUE of the furnace and how much energy you actually need. So to put this into the actual numbers of my home, if I need 17,452 BTUs per hour to keep it at 70 when it's minus 10 out, that's what I need. I need a furnace which can output 17,452 BTUs per hour. If I have more than that, that just means the furnace doesn't need to run constantly. But it doesn't matter how long it runs. It matters how much energy it's able to release compared to how much energy it's consuming. That's what the efficiency is. Runtime is entirely irrelevant. So that's one thing that I just want to make sure everybody understands. A furnace which runs for half, or a furnace which runs for twice as long because it's half the capacity is using the exact same amount of energy, assuming its efficiency is the same as the other one. So don't get tripped up on that. I don't really know how to put it other than that's not how that works. And I'm sorry that I didn't think to explain that in this video. I should have done that again. Now, HVAC in general is a very complex topic, and the video was over an hour long, but I was still taking things out because it was already an hour long. You can't communicate it simply, and that has led to a lot of people in the comments telling what I would call half-truths. I've said this before, I'm on record. Nuance on the internet is just like impossible. And one thing that keeps getting brought up again and again when we're talking about having an electric source of heat is, well, what if there's a power outage? My gas furnace doesn't work when the power's out. Okay, it has electronic ignition, an electronic gas valve, and 2 motors, the inducer and the blower, that need electricity to operate. So when the power goes out, my heat goes out too. Now the half-truth is that if I have a backup power system, I need less power on tap to heat my home with the furnace because all I need is enough electricity to power the furnace, and they're typically around 400 to 600 watts, somewhere in that range. Now, the reason why I call that a half-truth is that that reality only matters for those that are prepared enough to have an emergency power source. Many of you do, which is cool, but just having gas does not do you any good if you have a heating system which also needs electricity to run, which the vast majority do. Water heaters often don't, but that's also not even true anymore, depending on, my water heater, for instance, has electronic ignition. So when the power's out, it doesn't work. And the reason it has electronic ignition is because it has a blower motor to allow it to be vented through PVC rather than a metal chimney. I got excited when I saw that, thinking that it was a high efficiency water heater. No, it's just a way you can do it to make running the exhaust more easy. So I just want to put that out there. It is correct that if you have gas heating and you have a generator to power your home through a power outage, you need less electrical capacity to run your heat. But it doesn't mean you need no electricity to run your heat. You typically still need electricity. So just keep that in mind. Also, for people, this is not related to HVAC, but if you're holding on to your gas stove because of power outages, you can get a camping stove. That's always been an option. And as a matter of fact, if the stove is the only thing that you really care about, again, let's not wade into that. This is political enough. But if the stove is the only thing you really care about, any stove can be converted to run on propane. And in many countries, people have little bottles in the cabinet next to their stove that they just refill. So, if worse comes to worse, if the government comes to take your gas stove away, just convert it to propane, get a grill bottle, and be done with it. Anyway, let's move on. All right, and one thing that I need to clarify, I was actually gonna do this next, but I just realized I need to do this first, because the main reason I'm making this follow-up is what I will talk about after this section. But this section is on auxiliary heat, because I did not explain this well enough, and that's on me. A big part of what I did wrong was I said you can just whip out a bunch of space heaters if you're too cold. And a lot of people are taking that to mean that's what you do. That's the only way that you can live with a heat pump, which no, that's my bad. The reason I said that is because I like to empower people to solve their own problems. Space heaters are 15 to 20 bucks. And personally, I believe even if you have gas heat, you should have at least 1 or 2 space heaters on hand, because your gas furnace or boiler is a single point of failure. So it doesn't matter if the power's on or anything. If your furnace breaks, now you're SOL till you can fix it. And if you have a space heater, you can at least plug it in and keep one area of your home warm. So anyway, getting a bit off track there. That's why I said that. I like people to be empowered to fix their own problems, and I also want people to be prepared for emergencies. And having one space heater on hand, I would highly recommend people do. You have to be careful using them, of course. They have some dangers involved, but it is a form of redundancy that your gas furnace is not. But auxiliary heat is built into the system. It's not something that you would be chucking around with you. It's not something that is manual. It could be manual, depending on your system design. You could be okay with a manual auxiliary heating system, but by no means is that required. Heat strips, because a lot of people keep asking what that is. I don't remember if I even explained it in the video beyond a very simple description. So heat strips are just resistive wire elements that go into the air handler. They are typically, right now anyway in the US, they're available in increments of 5 kilowatts. The modern systems that I'm looking at seem to offer 5, 10, or 15 kilowatts of heat strips. Those are the electric form of auxiliary heat. Now they're resistive, so they are 100% efficient, but the heat pump can be more efficient than that. And I know that gets physicists really annoyed when you say more than 100% efficient. The coefficient of performance of a heat pump can be greater than 1, but electric resistance heating always works. So that's auxiliary heat form 1. When you have that auxiliary heat, then what's going to happen is if your heat pump fails, that will take over. So there you go. Now you have more redundancy than you ever did with a gas-fired furnace. Yes, if the blower motor fails, you're still SOL. But one of the things that's so funny to me about the fear-mongering over heat pumps is they're like, oh no, what will happen if your heat pump breaks? Well, actually, if you have auxiliary heat, you're in a better position than if your furnace breaks. But electric heat strips, that's what's hard about getting a heat pump, particularly if you're in a cold climate like I am, because that's a big power draw and you need to run a new circuit to it in almost all cases. Now, before I get into the operational paradigm of auxiliary heat, let me also just say that you don't necessarily need to have electric auxiliary heat. You can also have what's called a dual fuel system, which is basically a furnace and air conditioner, except the air conditioner happens to be a heat pump. So you will use the furnace as the air handler for the heat pump, and most of the time you will try to use the heat pump as your only source of heating. But if it becomes cheaper to use gas, which is, I don't really want to get into these weeds because that's even more weedsy than this discussion, but you can configure your system to kick on the furnace either when required, like the heat pump fails, or if it's cheaper, if you're using natural gas, or there's a whole bunch of ways you can set up a dual fuel system. That is an option. And going back to propane, to be honest, I am a little bit surprised we aren't seeing some movement towards local storage of propane. Because if you've ever been out in the country, if you've been in the country where there isn't natural gas infrastructure, a lot of people have these giant 500-gallon propane tanks that companies come and refill. I've lived with one before. It's expensive, but kind of interesting. But anyway, you have a huge amount of energy stored near your home in a tank. Now, I'm kind of excited about the idea if we want to electrify as much as possible, but we're worried about the grid and having a bunch of heat strips kicking on. Personally, I'm kind of excited about the idea of having a dual fuel system converted to propane and people potentially even just storing a few grill bottles in their garage because they hold a lot of energy. I think they're 20 gallons of propane. They hold enough to tide you over for like a day. The last time I did the math, I'm not doing it again. I'll put some numbers on screen. But I'm actually kind of excited about that as a dual fuel setup because the main reason why keeping yourself hooked up to gas is a problem is that the more you reduce your usage of gas, the more expensive your customer charges are. There's a minimum charge to being hooked up to gas. So even if you use none, you're typically being charged $25 to $30 a month just to have that gas line. So if the economics work out for you, which I recognize they don't in all places yet, but if the economics work out that a heat pump is cheaper than gas 99% of the time, and it only gets cheaper on those extremely cold days, over the year, it's probably cheaper to just kick your gas line out and then have propane as your emergency source. And there's a whole bunch of ways you could do it. You could convert a natural gas furnace to propane and have that be a dual fuel system. Or you could have propane little buddy heaters that are set up if you want to do it that way. There's a whole bunch of things you can do, which is why the space heater comment came up. The thing that honestly is just like baffling and kind of irritating to me is the idea that, oh, you're stuck. Like, oh, if your heating system goes out, you're gonna die. If my heating system goes out, my gas furnace is a single point of failure. I do not consider that to be okay. Now, I'm a handy person. I can clean the flame sensor. I can probably figure out why it stopped working, but a lot of people can't. And if they have a single point source or a single gas furnace, that's a single point of failure. So I would highly recommend if you are in anywhere that gets extremely cold to have a space heater on hand already, just so you can keep one room warm if your heat goes out. But anyway, the important thing is you have a second source of heat. The heat pump is not the only source of heat. In most cases, you may be able to get away with it being your only source of heat. And if you put a cold climate heat pump like the one my mom and dad got in a climate, I mean, honestly, even just in Southern Illinois, but anywhere south of the Mason-Dixon line, you really don't need heat strips anymore unless you want that redundancy, which to be fair, I think is good. But technically, your heat pump, their full output is available down to 5 degrees Fahrenheit, which is very cold. So if everybody has cold climate heat pumps, a lot of places heat strips aren't even necessary. But regardless of what your auxiliary heat system is, the operational paradigm is the same. So your heat pump will be your primary heating system until the point that it's no longer sufficient. So that's going to be either it's too cold for the heat pump to provide your only source of heat, which happens less and less as they get better and better, or you need more heat than the heat pump can put out. So that's why it's often called auxiliary heat, not just emergency heat. So for instance, where I'm saying if you have a heat pump that is sized right, meaning it's only outputting what you actually need, then when you're at those design conditions, you're stuck at that temperature. Except you're not, because the auxiliary heat will come on and boost total system output, potentially doubling it, to quickly raise the indoor temperatures. So I just need to address that. I did a bad job of it in particularly the long version of the video. I think I cleared it up a little bit for the second version based on feedback from people on Patreon. But that's how that works. Your auxiliary heat is a second system built in to your main air handler, and it will come on when it needs to, or you can force it on. So my comment about whip out a bunch of space heaters, I regret saying that, but we're gonna move on. Okay, and now, if you'll permit me, I am going to do a very un-Midwestern thing and toot my own horn. So my channel is called Technology Connections because the way my brain works is I need to know how stuff works so that way I can apply it to my life. And what I'm trying to do with this channel is have more people get into that mindset to understand that, oh, well, if this tool does this thing, then it can work in this way for this situation. And when it comes to HVAC stuff, I am not licensed to do any HVAC work. I've never taken any technical courses. I've never gone to do any legit stuff, but I am very well versed on the state of the industry, or not the state of the industry, the state of the manufacturing side of the industry, what equipment is on the market. And there's a lot of residential technicians who do not keep up with that. And unfortunately, that is causing them to quibble with little things that I've said because they aren't using the context of what's available to them now. So what was being fought against was you can't size a heat pump for heating because that could lead to short cycling in the summer. Now, that is only true if we're talking about single stage equipment, and less and less, or single stage equipment is going to be dinosaur stuff very quickly. So to define what that means, single stage means it's got one power output. That's what I have right now. I have a furnace which has one power output, and I have an air conditioner which has one power output. That's it. My thermostat is only telling it go or not. And when you have a single stage system, you do have to be careful about short cycling because you have to balance how much cooling capacity you can have with how much dehumidification capacity that will have. And that's based on runtime. Because if you have an oversized cooling system, that's when you do what's called short cycling, and it lowers the sensible temperature really, really fast, but it doesn't lower the latent heat load. It can't dehumidify, it's not removing enough moisture. So what happens is it gets cold very quickly, but the ambient humidity level doesn't really go down. And that can lead to mold problems. It's generally just unpleasant. It's nicer to have drier air in the summer. So you do not want to oversize cooling systems. Now, if we're talking about single stage heat pumps, then yes, if your heating load is twice as much as your cooling load, which is fairly common, then it could potentially be very bad to size your heat pump for the heating load because then it would short cycle in the summer. But single stage equipment is going the way of the dinosaur. Now, bottom line, we have dual stage equipment. So like my mom and dad's new heat pump, it is technically infinitely variable, but it's been configured to run on a normal 2-stage thermostat. So when it's calling for stage 1, it's actually only running at half of its capacity. I don't actually know that for a fact. It might be like 60%. I don't know how it's configured internally. But a 2-stage system actually does have 2 outputs. So if you are installing a heat pump and that home has ducts which are sufficient for a 4-ton heat pump, and that matches their heating load, but their cooling load is only 2 tons, you're fine. Install that 4-ton 2-stage heat pump. It will be a 4-ton heat pump in the winter when necessary, and you can completely lock out the second stage for cooling if you want, just to make sure it never short cycles. That technique, I feel like, is not well known yet. More fancier systems like Mitsubishi, they've got central ducted systems which are fully variable. Those are better, but they tend to have proprietary thermostats. So it's like, again, remember how I said this is complex? There's a ton to consider here. But if an HVAC professional doesn't understand that variable capacity means someone can oversize for heating and it won't be a problem in the summer, then they are not following the state of the art. It's that simple. They are not keeping up with what's going on, and they are operating on old advice or old knowledge. And that's what I'm battling against constantly, is both people in the general public who still think heat pumps don't work in the cold, and honestly, a number of professionals who still think heat pumps don't work in the cold. And then even those who understand that heat pumps do work in the cold, they're not getting that the modularity of these systems and the fact that they're very flexible, they can be configured in a whole bunch of different ways, means that nailing the size for cooling isn't necessarily that important anymore. And also, there's a lot of newer homes where the heating and cooling load is about the same. I don't want to make that a blanket statement, but my mom and dad's home, big single family home, 1,700 square feet, but it's got a full basement, so it's 3,400 square feet total. Only needs a 3-ton heat pump for heating, and it had a 3-ton heat pump for cooling. And my townhome only has a 2-ton heat pump for cooling. That's going to be fine for heating. But even if it's an older home that needs more heat than cooling, you totally can oversize the heat pump for heating so long as it can be modulated down for cooling, which these days, if they're not at least or 2-stage, they might be infinitely variable. So you have to be keeping on top of this stuff, guys, because if you're going to keep going out there and telling people, oh, you can't have a heat pump any bigger than this because it could be a problem in the summer, it might be true if you're talking about a bargain basement, single stage, very basic heat pump. But if we're talking about cold climate heat pumps or anything even just with 2 stages, you totally can change those factors around and make this fit that home better. So I don't know what to say other than you got to keep with it. That's all there is to it. You got to keep up with what's going on or you will be left in the dust. And with that, 2 more things to touch on, and then I will close this out. Let's talk about the shared walls situation. These comments will not stop. So there's a lot of people, I don't know how they thought this because I said at the beginning of both videos that I live in a townhome, and in the main channel video I said shared walls make it more energy efficient. I'm not hiding that. However, that doesn't mean I'm getting quote unquote free heat from my neighbors. That is not how this works. Again, sorry if that's blunt, that's not how that works. So the load on the structure, let me put it this way. Imagine you've got a house, right? That house needs whatever heating and cooling load it needs. You never count the internal walls of a house because they don't matter. It's the exterior walls that matter. If you took a house and built or cut it in half, like turned it into a duplex, then you have cut the individual heating needs of each half of that house in half, but the sum total is exactly the same as it was before you divided the house in half. So in a townhome, let's say it has 6 units, then there's 6 homes that all have their own heating and cooling loads. The end units are going to have higher heating and cooling loads, but the sum of them all is the same as if it was one giant house. And the reason why you don't have to count shared walls when you're doing load calculations is because it's safe to assume that on the other side of that wall, the heat is roughly the same. Even if it's not, even if your neighbors are going buck wild and setting their temperature up to 85, the wall is windowless. It's typically double insulated from what I understand. I know that to be a fact for my home, but based on other comments, it seems to be pretty common across the country. And so even if my neighbors were set to 85, I have one additional wall with insulation that has a 15-degree temperature difference across it. Very, very little heat is going to move in. Or let's say my neighbors on the other side, they left and they turned their heat down to 55. Well then, that wall, that insulated, windowless wall, now has a 15-degree temperature difference across it, and some heat from my home will leak into theirs, but it's very little. You know what it's like when the weather outside is 55 degrees. You barely need any heating at all. So in my case, it's that I have one wall that's behaving as if the outside temperature were 55. It's not meaningfully contributing to my heating loads at all. So yes, it is energy efficient to share walls, because that means I only have, I have two fewer exterior walls. I have less loading on my home. That's why it's energy efficient, but it doesn't mean that I'm getting free heat from my neighbors. That wall has very, very little thermal gradient across it, which means very little heat is going to move across that wall. And if it's anywhere close to the same set point, effectively zero heat is going to move across that wall. So just to clarify that, I wasn't pulling a trick on you. I was very upfront about it, but B, it's not a gotcha. That's just how it works. That's just what happens when you share structures like that. When we're talking about apartment buildings, things get really wonky because you've got other units on all sides and you only have one wall, which is a load, unless you're on the top floor. So you often have situations in apartment buildings where you don't need any heat at all, because if everyone below you is setting their heat higher than you want it, it's all just going to end up getting into your unit, and you got heating on all sides. But with a townhome, you have at least two exterior walls plus your own roof section, so you're only saving the two side walls. And if you're on an end unit, you're not even saving as much. So yes, the shared walls thing, I don't know how to put it other than that's not how it works, because that's not how it works. Okay, and then the last thing that I want to respond to as far as feedback on the main videos was this very common comment that like what I'm suggesting would lead to your heat running quote unquote all the time. Now, I will assume in good faith that some people are saying this when only talking about design conditions, but I think a lot of other people are forgetting that that only happens at design conditions. So yes, if I have a 2-ton heat pump, which is actually still technically a little oversized for my home, but if I had a 2-ton heat pump that needed to run constantly when it gets to -15 outside, that's when it needs to run constantly. The rest of the year, it will not be running constantly. So just to put that out on the line, like, I don't know if there's a miscommunication or misunderstanding there, but it would only ever run constantly at design conditions. The rest of the time, it's going to run occasionally. However, and this is where there's more nuance to be discussed here, when we're talking about air conditioning systems, the compressor has lubrication going on. It is very much like an engine in a car. There is an oil sump. The compressor, the big black thing, is just a bottle, basically, so you can make connections more easily and everything is sealed. So it's a bottle that's holding the actual mechanical compressor inside of it, and at the bottom is a big puddle of oil. The electric motor is usually sitting in that oil, which helps cool the windings, and there's an oil pump which actually sends that oil into the scroll or piston of the compressor to lubricate it. So just like a car engine, every time the compressor stops, oil will drain out of the compression area, the scroll or piston, and end up in the sump. And when you start it again, it briefly runs dry. It only has the film, whatever's left over from the lubrication, until the oil pump actually starts sending oil and to the various places it needs to go. That means you want to minimize the number of starts, That's why short cycling is not just bad for humidity, it's bad for equipment. Because if you're only running these like 5-minute cycles, then it spends a lot more time running without proper lubrication than it would if the cycles were longer. And modern inverter-driven equipment of the fancier variety strives to never stop. It will just slow down the compressor to match loading. And the only reason it stops is if the load is lower than its minimum output. So the mini split heat pump that I installed in the garage at my old place, that heat pump runs at any arbitrary capacity between some minimum level and its maximum level. And if it actually has a heating load or cooling load that's above its minimum level, it doesn't stop. It just slows down and keeps running just a little bit. That's how this is going to work. That's actually healthier for the compressor, and the other mechanical parts, the blowers basically, they also slow down too. So I can't speak intelligently on how the wear works with like fan motor bearings, if it's better to have them constantly spinning. I can see arguments either way, but this idea that it's bad for the equipment to be running constantly. First of all, it only will ever run constantly. Well, no. First of all, a lot of equipment does actually strive to run constantly now because it's better for comfort and also it's better for the compressor's longevity. But second of all, it's only ever going to do that on design conditions. So yeah, I don't really know what happened with that, why I'm getting so many comments that are saying that it would run constantly. First of all, it's not going to run constantly outside of design conditions. It just won't. Like, I don't really know how I could have foreseen that to be a thing people would believe to be the case. But I think that's just because I have a very, talking about HVAC stuff and energy and how the system actually needs to run, I get that on a very deep level, and I imagine most people don't. So this is just one of those things where I failed to recognize that my own knowledge is not common. That happens a lot to me, unfortunately. But even setting that aside, a lot of newer equipment does actually try to never stop. So that's just not a thing you need to worry about. Like, I don't want to just say trust me, because like, what is that? What good is that? I'm just some schmuck on the internet. But that's the reality that we are running into now. A lot of systems, particularly when we talk about like VRF systems, which are really fascinating, but you're not going to see that in residential applications. At least I highly doubt it. But a lot of these systems now, they're basically running all the time, and they're just trying to move heat around as efficiently as possible. The VRF systems, that stands for variable refrigerant flow, which technically, I guess, an inverter-driven compressor, you could call it that, because the compressor can, but what they mean by that is you can actually, and this is really cool, so a lot of apartment buildings now, if one unit wants to be heating and the other unit wants to be cooling, rather than just suck the energy out of one apartment and throw it outside, it gets moved to the apartment that wants heat. So heat is actually being moved around the building using these new VRF heat pump systems, which is really cool and really fascinating. And those systems especially, they're much more complex than a single zone residential system or even like a multi-head mini split system. But that's the sort of stuff that that's the cutting edge of the industry. We are talking about equipment that is almost magic. It's able to take energy from one apartment and put it in a different apartment. So rather than needing to actually waste that heat and get it outside, you can just move it, which is so cool. Yeah. So in those systems, I'm not that familiar with them, but they have the actual amount of heat that the outdoor unit is rejecting or accepting is based on the total load of the building. So let's just say there's 10 apartments and 6 of them want heating and 4 of them want cooling. Well, then what's going to happen is the outdoor unit is only pulling in a little bit of heat because on balance, it needs to add a bit of heat to the building. But the 4 units that want cooling lower the amount of heat that it needs to add. So it's just adding a little bit, and then it's taking the heat from those apartments that are requesting cooling to fill in the gap. I hope that makes sense, because they're really cool. So yeah, this notion that the heat would run all the time based on the correct sizing is A, not real, because it would only run at 100% output at design conditions. The rest of the time it's going to run at something less than 100, often less than 50%. Also, a lot of systems actually do want to keep running all the time because it's better for the compressors and often more efficient, particularly when you have multiple staging and variable output. And then it's also just, I don't know, that's a really weird one. I don't know how I could have predicted how that would go. Short cycling is also a problem for a furnace, because with, and I know those of you in countries with boilers, like, furnaces are baffling, but they go from room temperature to having fire in them back to room temperature with every cycle. That's a lot of thermal stress. And if it's going through a thermal cycle 40 times a day instead of 10, that's also not good for it. So you cannot give a blanket statement that says it's bad for equipment to run longer for so many reasons. And it's also not even what would happen assuming a single stage equipment on days with design conditions. That one's just, I really don't know how to tackle that one other than to just say, here's how it actually is. Hopefully that helps you. Yeah, so that's pretty much it. Now, I know I'm paying too much attention to comments. However, this is a very important topic that we need everybody to understand, especially professionals who are dealing with this stuff, because this is the future. I know there's probably going to be some people in the comments who are talking about how it's not the future, but this is definitely the future. The future is electric, and heat pumps especially are a way that we can use less electricity to get more heat. They are only going to get more flexible, more efficient, and more appropriate for all climates. So yes, this is important that people know. Unfortunately, this is all very politicized. Somehow, there are people that think climate change is a hoax. Now, I don't even bother addressing that anymore because too bad. Like, I just pretend we're all on the same page there because we all really should be on the same page. So I don't even bother getting into that. But definitely, heat pumps have been politicized, and it's really hard for me to get past that. I'm trying my best to just throw out on the line that they are obviously, setting all politics aside, let's just pretend for a minute that we didn't have pipes of methane coming into our homes. Let's pretend for a minute that electricity was how we did everything, because just as a reminder, electricity is how we do everything except heat our homes, create hot water, maybe run your dryer if you're in America and that's a thing we do, and then have a stove. Electricity can also do all those 4 things, in addition to lights, your computer, your game console, a fan, your smartphone, increasingly, your car, lawn tools. There's so many, I don't know if you've ever looked at some of the battery-powered lawn equipment that's available now at Home Depot for not that much money. It's really impressive. And that's the direction things are going in, and electricity can do anything. So obviously, we're going to use more and more things that are electric, and a heat pump is a way for us to use less electricity and get more heat. That just makes sense. You're always going to want that, and particularly in parts in the US where most people have air conditioning, it's just utterly bonkers to not have heat pumps be standard, because air conditioners are heat pumps. It bothers me so much that I have a heat pump, but it only pumps out. It can't pump in. So it's a paperweight for 6 or 7 months out of the year when it doesn't have to be. It could be my source of heat too, and it would be cleaner, especially here in Illinois because we've got so much nuclear power. But even with an entirely fossil-powered grid, because heat pumps can get more energy from the air than it takes to run them, they emit less than burning gas locally. in most cases. And on a year-over-year level, certainly they do. There are some days where the heat pump would be worse emissions-wise than just delivering gas to your home and burning it. But most of the time, it's better, which I didn't even address that. I don't know how so many people are in this place that you need a solution that works all the time, and that's the only acceptable solution. If there's a better solution in 98% of the time, but that 2% of the time needs something to bridge the gap, that doesn't invalidate the solution. That's but sometimes coming up yet again. So yes, it's just like heat pumps are going to be a thing, okay? All you in the HVAC industry who are curmudgeons about new things like variable speed blowers, electronic expansion valves, the fact that you have diagnostic tools you might need to learn how to use rather than just hooking up your gauges and charging to subcooling, you gotta get with this stuff because it's going to happen. And if you don't know what you're doing, you're going to have your competitors give lower bids who are actually going to give the tools that people want in their homes. They're actually going to hook people up with that because they're not afraid of it. So I'm sorry if this feels like paternalistic, but I'm literally at my wit's end here that the professionals in this industry are afraid of new technology. We used to be a country that liked innovation. We used to like things improving, and we used to keep up with them. But now somehow we've gotten in this mindset where people heard from their uncle out in Tuscaloosa that some guy had a bad experience with a heat pump up in Minnesota, so clearly they're bad. That's just the state of the world right now, and it hurts. And I'm trying my best to make it better. So thanks for watching.